Yeah, so I'm going to talk to you about quantum chaos for 3 lectures. And this is a subject that has an old, rich literature, both in theory and experiment, but has seen, from my perspective, a sort of revival of interest recently, drawing in a number of different directions. And so we've already heard from one about chaos in black holes, also from Alexei about chaos in SYK. So what I'm going to do is actually present you a picture of quantum chaos from early time to late time in the context of spin chain. So a very concrete spin chain. And I'm going to show you how all the different manifestations that you may have heard about, from out-of-time world correlators to the late-time dynamics associated with eigenvalue level spacing statistics, how it all arises in this spin chain. And so this touches on a lot of different questions related to how and when isolated quantum systems thermalize, questions about how quantum information spreads and becomes effectively lost as time evolves, and questions about, are there bounds on quantum dynamics? These are all intimately tied up with the question of quantum chaos. And so there are a lot of different connections that one can make, including to classical chaos. You can make connections to the foundations of statistical mechanics, to random matrix theory, to experiments in which time is effectively reversed, to entropy and decoherence. And then the newer things that have come into the story are the dynamics of black holes and quantum gravity, new experiments with new kinds of highly controlled quantum many-body systems in the context of cold atoms, trapped ions, superconducting qubits, and other sorts of interesting systems. And in particular, from my perspective, a focus on quantum information and the role that it plays in quantum chaos. And so that's what I'm going to talk about today and tomorrow and on Saturday, is sort of quantum chaos from the perspective of quantum information in the context of a simple spin chain. And I'm going to give you it's going to be a sort of phenomenological discussion of quantum chaos. So I prepared lots of numerical demos where I'll just show you data for spin chains of about 12 sites, and you'll see in completely explicit detail all the gory details and physics of chaos in these spin chains. And there will be a set of lecture notes made available. They're not quite ready for public consumption yet, but hopefully by the end of my 3rd lecture, I'll release them, at least in a beta version. And along with these lecture notes, I'll release all of the numerical demos. So they're written in MATLAB right now. Actually, if someone's interested in rewriting them in Python or Julia, I'd be happy to talk with you about that. You can get an acknowledgement. So you can take these demos home. You can play around with them yourselves. You can adjust the parameters. You can make them run faster. These are sort of simplified, scaled down versions of code I use in my own research. I've tried to make it sort of as readable as possible, so some elegance has been sacrificed. But in the event, it's something that you can use to get a sense of the physics in small size many-body systems. Okay, so the first lecture today will be sort of a survey, which is sort of what I just did, some discussion of classical chaos, just to orient ourselves, the basics of quantum many-body physics, and then a brief introduction to quantum chaos. Okay, and then the second lecture will be about early times. And the third lecture will be about late times, and something about experiments. So I'll actually tell you a little bit about what the state of the art is, and a little bit about what has been done in the past in this direction. Okay. So this is essentially the plan. And it's a little fuzzy. We may get further into early times in this first lecture. It depends on how fast we go. And yeah, so that's the idea. Okay. So let me start out by setting up the basics. Okay, so let's talk about quantum many-body physics. This is probably going to be remedial for most of you, but I want to, because there are many different levels, I want to just have one clear starting point. So the most basic object, quantum mechanical object, is a qubit, or a spin-half, a two-level system. And this two-level system can be taken to have a basis, which is labeled by 0 and 1, a binary basis. And this is a space, this is the basis for the space of states. And in terms of this basis, I can write down the basis of Hermitian operators, which are just the Pauli matrices. So sigma x in this basis will be like that. Sigma y will be with the I. So this is completely standard. Sigma z is 1 minus 1. So in particular, I have the relation that sigma z acting on A is minus 1 to the A. Like that. For A equal 0, 1. So in the conventional language, 0 is spin up and 1 is spin down. So I'll use this notation, a plus or minus sign along with the Cartesian coordinate to indicate that it's plus or minus spin in that direction. Okay, so this is something you all know. Now then, I can go to the case of n qubits, or n spins, and I'll kind of use this qubit spin language interchangeably. To some extent, I use the word qubit to emphasize sort of the information theoretic aspect of the discussion. But in a particular physical instantiation, the way these qubits may be realized may be as actual physical spins or via some other two-level system. So don't worry about angular momentum in this story. This is just sort of algebraic at this stage. So I have a space of states, curly V, and there's a basis for this space of n qubit states, which is given by the set of all combinations of single qubit states. So this is just a tensor product. And here A takes values in 0, 1 to the n. So this is the basis. So I just take, this basis for every single qubit, and I have a similar basis for all n of my qubits. And so the dimension of v to the n is 2 to the n, because each of these AIs can be either 0 or 1. Okay. And in terms of this basis, I can have a pure state psi, which is some arbitrary linear combination of the basis states, or I can have some density matrix, which is an arbitrary combination of all of the Brausenkets like that. Okay? So again, this is meant to be elementary, but just so we're on the same page. Okay, and similarly, I have operators. And the elementary operators, the operators which generate the whole algebra, are the single spin operators, which I'll denote like this. So here you should think of this as a site index or a qubit index. Site or qubit index. The lower subscript r. R is supposed to stand for space. And this is x, y, or z. It tells you which Pauli operator you have. And the meaning of this operator, sigma r alpha, is that it's an identity on the first Then at the rth position, I put sigma alpha. And then I go out again like that. So it means this big tensor product of operators, but I always just write it in this abbreviated form like this. Okay. And these operators obey a version of the spin algebra, which is that if I take the Pauli operator for spin r of type alpha and for spin r prime of type beta, then this is delta r prime so they commute unless r is equal to r prime, and if they're on the same site, then their algebra is just the algebra of Pauli matrices. Okay? And the other thing that I'll remind you of, you've already seen a very nice introduction to this in Aaron's talk, is that we have a notion of entropy. Given a mixed state rho, we can compute the von Neumann entropy of rho, which is defined to be the trace of rho log rho. And here I'm going to use base 2 just to irritate you. So in this base, the entropy of one two-level system, which is maximally mixed, is 1 bit. Okay, so this is like the entropy in bits. And if you don't like it, just multiply everything by log 2. It's not a big deal. Okay, and this is sometimes called, this is the von Neumann entropy. It's sometimes called the fine-grained entropy or the entanglement entropy, depending on the context. We'll see more about that later. Okay. And the other thing that I'll say is that we could also, it would be very useful for us to consider subsystems. A and B, which consist of NA qubits and NB qubits such that the total sum is N. So I take NA of my qubits and put them in one group and NB in the other. They add up to N. And I can always take the state of the whole system, rho AB, and produce by a partial trace the state of just A. So this is, again, a concept you've seen already in various talks on entanglement. I just remind you here that this is something that we'll do a lot. Okay. And this is a little dry. We're almost done. I want to tell you a little bit about dynamics and then discuss the actual Hamiltonian and start talking about chaos. Okay. So, of course, dynamics, we have a Hamiltonian H. Say the Hamiltonian could be time dependent. That's something we could allow. But in this course, I'll restrict myself to informationally isolated systems. So no information will be exchanged with an environment. I may control the system classically by turning a field on and off or something, but that doesn't couple to an external quantum mechanical system. So this is the Hamiltonian. And time evolution is generated by a unitary operator, U of t, which is just the exponential. Right? And so we know states go to U psi, and density matrices go to U rho. This is the Schrodinger picture. It'll also be very useful for us to consider the Heisenberg picture, in which operators evolve. An operator W has a Heisenberg form, which is U dagger WU. Note the difference between the daggers on the state and on the operator. Okay, and then superposition, entanglement, positive operators, projectors, unitaries, all that stuff about quantum mechanics is still true here. This is the setting. Okay, and in the notes that I'll post, there are lots of little exercises to familiarize yourself with this setting if you're not already. So now I want to talk about the kind of Hamiltonians that we'll consider in this course. And I'm going to define a Hamiltonian which I'll call the power law quantum Ising model, which henceforth will be referred to as the PQIM. And this model takes the following form. It's defined on n qubits with open boundary conditions, and it has structure like this. First of all, there's an interaction term which couples different qubits in the Z basis. So I have a sum from L equals 1 to L naught, and a sum from R equals 1 to N minus L of sigma ZR, sigma ZR plus L. There's a coupling constant J and a factor of L to the Greek letter zeta. So what is this Hamiltonian? It says, this term says that the spins they get lower energy if they align in the Z basis. And there's an energy cost associated with spins of different distances apart. The separation between them is L. And the coupling decays like 1 over L to some power. So for example, and I allow this power law to decay to go over a distance L naught. So if, for example, you take L naught equal to 1, you just get a nearest neighbor interaction. Right, so the physical picture is I have some spin chain, and I have a spin, say, sigma 1 Z here, sigma 4 Z there. This corresponds to L equals 3 because it's 3 neighbors away. And the interaction energy associated with this is 1 over L to this power zeta. Okay. So that's the thing that's actually the only term which couples the spins in our model. Now the other term, you'll have two other terms. One is what's called a transverse field term. So let me just, the terminology, this is an Ising term because it's like a spin-spin interaction, but it only involves the components in one direction. So that's why it's called Ising. It's exactly like your classical Ising model that you've seen in statistical mechanics. I have another term which now involves the spins in the x direction. I have a coupling constant h sub x, and I just simply sum over h sub x with all of the Pauli operators in the x basis. So what is the physics of this term? Well, if we ignore the first term here, this term just wants all the spins to align in the x basis. Okay. But recall that x and z don't commute, so that means there's a competition between these two terms. And so if I'm thinking about in the basis of this term here, which is the z basis, then this Pauli x flips me from spin up to spin down. So we say that this term causes quantum fluctuations in this basis. It causes the spins in the z basis to fluctuate, to flip from up to down, and vice versa. Okay. And the final thing that we'll add is a z field. So this is now something which wants the spins to polarize in the z direction. There are two terms here. One of these terms is a fixed r-dependent z field. And this is random, in principle, random disorder. So when I turn on this last term, this is like saying I could have a random local field in which I randomly want the spins to point up or down with some energy cost measured by h hat. Okay, so I distinguish between these two terms. This is a fixed term, it's the same for every Hamiltonian. In principle, I could introduce the notion of randomness or disorder, or I consider an ensemble of Hamiltonians. An ensemble is defined by having different values of this parameter. Okay? And that's the model. I'm gonna take this model and we're gonna study it to death. And the parameters that we'll use for this model, well, they'll vary a little bit. But mostly, I'll consider the following parameters. I'll take J to be equal to 1, which means I'm measuring all energies in units of J. I'll take zeta to be 6. That's the coefficient of the power law here. This is just sort of random. It's eventually motivated by a Rydberg experiment, but don't worry too much about that right now. Hx 1.05. Hzr is 0.375 times minus 1 to the r, and h hat 0. So this will be mostly what I use. So what does it say? I have some interactions which decay pretty rapidly. So the interaction between different neighbors is decaying relatively fast. There's a sizable quantum fluctuation compared to the coupling between them. They're all of order 1. And there's a staggered Z field. So if I added a Z field which polarized you in one direction, preferably that would, that you can do that, and that's interesting. But this is a little bit more chaotic, it turns out. So let me explain a little bit why this funny choice of parameters and what you should take away from this. Quantum chaos, we think that for a broad class of Hamiltonians, quantum chaos is sort of universal in the sense that if I change this parameter to 0.4 or 0.5 or change this to 5 or to 7 or change this to something else, that it would still be chaotic. And all of the essential features are the same. However, here I'm going to be considering system sizes which are, say, 12 to 14, so that I can do some exact diagonalization on my computer and actually show you the physics of this model. And when you're in this small size system, it's important, well, let's say it this way, finite size effect can sometimes obscure the physics that you're interested in. So I've chosen these parameters so that they highlight certain features of the physics that we believe are generalized to large systems. However, I'm going to be careful to sort of point out places where we're actually not sure what part of the physics carries over to large n. Okay, so that's why I chose this particular model, because it sort of illustrates the basic points I want to make in a very clean way. But you can check, I encourage you to do so with the code that I provide, that you can adjust the parameters and nothing changes very much. Okay, so this is a claim I'm making that you can check. The other thing I want to say about this thing is that it's few body. What does that mean? It means that every term here involves only a few spins at a time in the interaction. You may have heard the phrase K local. I think Juan used this phrase. K local means that the Hamiltonian may be written as a sum of terms, each of which contains no more than K of these Pauli operators. So here this Hamiltonian is 2 local because this term contains 2 spins at a time. This contains just 1 and 1. Okay, it's few body and it's also geometrically local. Meaning that spins mostly talk to their neighbors and not to very far away spins. So later on in lecture 2, we'll see an example of a non-local Hamiltonian, because I want to explain to you how the timescales differ in that case. But mostly we'll focus on this local Hamiltonian. And so the few bodiness is a sort of more or less generic feature of all physical systems. You could try hard to engineer a non-few body Hamiltonian, but it's very difficult. So this is sort of almost always true. And what really matters is whether it's geometrically local or geometrically non-local. Yeah. Good question. Yeah, so I'll take it to be 5. Yeah, again, I encourage you to play around with it. You'll find that it doesn't change things that much. But there's a reason why I chose this, and I'll explain that next time. Other questions about the setup? So I emphasize, like, I like this because this is like a completely concrete thing. It's just a matrix, and you can just put it in your computer and see what happens. Like, imagine that you're an ion trap experimentalist, and you have 12 ions and perfect control. What is the physics of this system? Yeah.
So you're taking L0, 5,
Yeah.
and you're going to consider n equals to 14.
Yeah.
Can you really say it's p-body Hamiltonian when it's half the system almost?
Good question, great question. So the few bodiness, in my definition, never cares about how far away they are. But geometrically local, yes, I will call it that because of the high power here. So there's a question about if suppose I made the power 0 or 1 or something, so it's like a really long-range interaction. Then I might not be justified in calling it local. In fact, to really be strictly correct, it's only really local if they really turn off after some distance. However, this thing is sufficiently small that the power is sufficiently high, things decay sufficiently rapidly, that there's not much of an effect. So even on the 3 sites away, it's 3 to the 6. It's really small compared to the nearest neighbor coupling, and so it has a very small effect. I'll comment more about what this does. And you can check in the code I provide that if you just put this to infinity or just take L naught to be 1, that most of the physics is the same. And actually, I'll explain to you a little later in the next lecture how you can diagnose whether it should be called local or not. Basically, it's whether information propagates ballistically or superballistically. Okay, so let's talk now about thermalization and chaos. Okay. Before I do that, actually, let me talk a little bit about timescales here. I guess I should keep this down. Because this course is organized by thinking in terms of timescales. So we're going to start at early times and go to late times and see how chaos manifests in different ways. And in this model, there are various kinds of timescales that you can have. The simplest kind are timescales of order n to the 0. So that's something that happens in a time of order 1 in the units, say, where j is equal to 1. So like if you make a local perturbation, that may decay locally in a time of order 1. This is like a local perturbation. Now you could also have ballistic motion or diffusive motion, where a particle at one end of the chain needs to go to the other end of the chain. And that might take a time which scales like order n or order n squared in 1 dimension. And this is ballistic or diffusive motion. But then there are still longer times that are relevant. There are times of order e to the n, which is associated with the splitting between different energy eigenvalues in the system. This is energy level splitting. And then actually one can contemplate even longer times of order e to the n, which is a recurrence time. We know almost nothing about things on this time scale for large systems. We know almost nothing about things on this time scale for large systems. We're pretty knowledgeable about things that scale like a power of the system size. So lecture 2 will be primarily about these time scales here, and lecture 3 about these time scales here. Yeah?
Is it known that the story ends there, that there's no higher exponential order relevant timescales?
No. At least I don't know the story ends there. I mean, you do have a recurrence on this time, so you come close to the initial state again. but maybe there's some structure on an even longer time scale. It's not clear where that would come from, but I really don't know. So, okay, let's talk about thermalization in chaos. And so what is thermalization? Well, let's imagine we have this Hamiltonian, and we take two different initial states. Psi1, which is all up in the y direction, and Psi2, which has the first spin down in the y direction, and all the remaining up in the y direction. Okay, so these are two states. You can check that both Psi1 and Psi2 have average energy 0. You just compute the expectation value of Psi1 and Psi2 with this Hamiltonian, because the expectation value of poly z and poly x is 0 in the y basis for any definite y state. So expectation value of psi I, HP, psi I, 0. So they have the same energy, same average energy. They differ only by one site, but they're orthogonal states, right? They're completely distinguishable. You just need to look at the eigenvalue of sigma y on the first site, and you can tell them apart. But what happens if we evolve the system in time? Let's plot here the expectation value of sigma y on the first site. If you evolve state 1, what happens? Something like this. This is plus 1. If you evolve state 2, you get something like that. So this is the evolution psi 1 of t. This is the evolution psi 2 of t. And so what we see is the following, that if you start out with perfect distinguishability as far as sigma 1 is concerned, sigma y on the site 1, then as you evolve in time, because this system is chaotic, because it thermalizes, the expectation value decays in magnitude closer and closer to 0. And at late time is very close to 0 for both psi 1 and psi 2. So what that means, as far as this observable is concerned, is that at late times it can't tell psi 1 and psi 2 apart anymore. So in other words, as far as sigma 1 is concerned, psi 1 and psi 2 are now indistinguishable, or the memory of the initial condition has been lost. Okay. Now, of course, psi 1 and psi 2 in their time-evolved versions remain exactly orthogonal. They're completely distinguishable as quantum states. But as far as simple observables are concerned, as far as observables like single Pauli matrices or few Pauli matrices are concerned, they're indistinguishable. And that's what thermalization means in practice, is that you cannot distinguish these two time-evolved states using only simple observables. It means you lose memory of the initial condition as far as operators like single Pauli matrices are concerned. And moreover, what is this final value here? Is this value special? Why is it 0 and not 0.5 or minus 0.5? Well, this value turns out to be the value of the thermal ensemble at the same average energy. So I encourage you to check that the infinite temperature state, which is the identity matrix on all n, normalized by 1 over 2 to the n. This is the infinite temperature thermal ensemble. I encourage you to check that this state has average energy 0. That's pretty clear because these are all traceless. And since it has the maximum possible entropy it can have, it's a thermal state with that average energy. That's the definition of a thermal state. It's a state of maximum entropy consistent with a given energy. So this is the thermal state, which is associated with the average energy that both these two states possess. And in this thermal state, the expectation value is equal to 0. So thermalization means that no matter what initial condition you start with, simple observables decay at late time to the thermal value. It means you lose memory of the initial state. It means you generate effective entropy, because this state has entropy. These states have no entropy, no fine-grained entropy, but this state has lots of entropy. And so this is what I'm going to take to be the essence of chaos. Chaos is sort of about the way that information spreads and becomes lost as the system evolves in time. Okay, that's kind of the organizing principle of these lectures, is that chaos is about information spreading and information loss, in particular about quantum information spreading and loss. And we'll see how all the different things you think about in terms of chaos, or at least some of them, are related to this point of view. So I'm going to make a quick survey now, and then we're going to go to the slides, and I'll show you some data for what really happens. This time scale is a time of order 1. So this is like, I don't remember, I'll show you in a second what it is, but this is like t equals 1, something like that. So this decay happens in a time of order 1. And so you can already see the questions you can ask. How long does this take? Are there other observables that it takes longer to thermalize? How long does it stay thermalized? How well thermalized is it? There are all kinds of questions you can ask. And all of these questions relate to different properties of chaos in the system. Sorry, what's the definition of what? Oh, it's the identity operator on the n-qubit Hilbert space divided by 2 to the n. So it's just identity matrix. Normalized so its trace is 1. Well, so it's not, let me be a little more careful. This is the temperature equals infinity. So recall the thermal state is e to the minus h over t. Normalized repetition function. So if I take t to infinity, then the exponential becomes identity. And so I just get identity, and then the trace, which normalizes it, must just be the total Hilbert space dimension, which is 2 to the n. Does that make sense? What I'm claiming is that the result, well, so this is, what I'm saying is that if you look at the late time value of this observable in these 2 states, it's the same as in this state. That's an easy claim to check. What I would claim furthermore is that, and I'm not going to show you this explicitly, but if you look at other observables, suppose you look at sigma y on site 5, or sigma x, sigma z on some other pair of sites, they would also reproduce approximately the expectation value in this state. And so the claim is that for some set of observables, and we'll be more precise about what set of observables, for some set of observables, actually all the expectation values at late time will be approximately those of this state. Sorry, Frank? No, that's chaos. Yeah, but so these trajectories diverge and they go around in phase space and everything gets complicated and fuzzy. You visit every point or come near many different points. That's like thermalization. Okay, yeah. There was another question? Oh, this is, I'll show you actually the data for this. This is just the expectation value in this state as a function of time. I didn't do anything else to it. So quantum chaos, my perspective is that it's sort of the spread and effective loss, because you don't actually lose information, effective loss of quantum information. And this can be connected in various ways to all kinds of different aspects that you may be familiar with from classical chaos. So, yeah.
Now I'm getting confused with this. There are systems that thermalize but don't show chaos. So are you
Well, no, I don't necessarily claim they're exactly synonymous, but this is my perspective on chaos. And I think if you have a system that you really say thermalizes but doesn't have chaos, then that would be interesting to me. And I want to understand exactly how thermalized it is and exactly how non-chaotic it is. And whether there's really a sort of overlap in what I'd want to call chaos and non-chaos. So I'm going to talk about, maybe I should say, I'm going to talk about quantum chaos from the point of view of this way of thinking about things. And I'm not going to claim they're exactly the same, but I think it's a useful perspective to take on the phenomenon. And if you really have an example where you think that they're different, I'd be very interested in hearing more about that. Yeah?
For you, the opposite of chaos is like many-mode organization?
For example, yeah. And I'll speak about that a little bit later.
This depends on the state. I mean,
Yes.
the evolution is usually highly so if you take an eigenstate of the Hamiltonian, you have not such.
Yeah. So then, if you had an eigenstate, in order for this to be correct, I mean, there's no evolution. It would have to imply the eigenstate itself already looks thermal, for example. And that's a statement that's related to chaos. Again, I want to emphasize there are lots of different possible definitions of quantum chaos. There's no, as far as I know, universally agreed upon way of thinking about it. Eigenstate thermalization, which is about the properties of eigenstates, this kind of information loss or memory loss, random matrix theory, Lyapunov exponents, there's lots of different approaches, and it's not clear how they're all related. So I will talk about, in the next two lectures, attempts to define, this is sort of the perspective, if you like, but in concrete terms, we'll think about attempts to define quantum Lyapunov exponents, and I'll explain more about what that is in a second. We'll talk about Loschmidt echoes, time reversal experiments, something that Horacio Paskowski in the audience was a leader in, is a leader in. We'll talk about random matrix theory. And, we'll talk about actually experiments. How in practice we try to probe and measure chaos, old and new. And I'm going to try to approach it all from this information theoretic point of view, and we'll see how far we get. Okay, so now I'm going to switch to the slides to show you some numerical data. So here is the Hamiltonian again that I showed you on the board. The parameter is all as I claimed. And so let me show you a picture of thermalization, which is what I showed you before. Oh, whoops. So here's that picture. This is a plot of the expectation value of sigma y on site 1 in these two different initial states as a function of time for 12 spins. Okay. I have open boundary condition. Yeah. And you see in state 1, so the blue curve is state 1. It starts at value 1. It sort of oscillates a little bit, and then it quickly kind of has some, it gets close to 0, and there's some residual oscillation that happens at late time. Yeah?
If you pick your spin to be plus minus 1 in the bulk, would you see the same thing?
You would see the same, yeah. They would sort of, the states would look the same for a while. If you flip the spin at 1 and measured the spin in the middle, they look the same for a while, and then they would eventually deviate, and they would both approach 0. Okay, so they'd sort of they start decaying, and then they kind of differ a little bit, and then they both approach 0.
If you take away one of the terms of Hamiltonian,
Depends on which term you take away. If you remove this term, it'll still happen less effectively. So if you remove this term and you make this nearest neighbor, then that's integrable. That's the equivalent to free fermions and doesn't thermalize in the strong sense that I mean here, and it doesn't display chaos. However, if you have just nearest neighbor and both of these terms, that is chaotic for generic choices of these interactions, and you would still see this. If you remove the interaction, then of course nothing happens. Everything just oscillates on single sites. Okay, so here is, again, this expectation value is a function of time. You see already interplay different time scales here. There is the time for this initial decay to happen to approximately the value of the final oscillations is of order 1. I mean, here maybe it's 5 time units. But it's some time of order 1. It's not growing system size. And you can check that. You can change the system size and see that it doesn't change substantially. You see there's some residual oscillation because this is not going to be exactly 0 because it's a small finite size system. And you can ask, okay, this is at short times, what happens at longer times? And that's what this plot shows. So now I show the same thing, again for 12 spins, I think, the expectation value of sigma y on site 1, out to times that are equal to 2 to the system size. So I guess this is maybe 10 sites. And so you see, okay, the fluctuations are a little bit larger than in the previous slide because I made the system size a little bit smaller. But for all this time, nothing happens essentially. You know, there's like little spikes and fluctuations, but thermalization persists out to this very long time in the system. Okay. So nothing's happening on at least exponentially long time, even for 10 spins. And so one of the questions we'll try to ask is what's going on in this intermediate? Is there anything happening, and how do we diagnose the dynamics of the system during this time period?
Okay. So is it important that it's observable that distinguishes the two states that you're looking at? Is really, it tells you nothing about the energy, is uncorrelated with the Hamiltonian operator?
Yeah, so if the perturbation sort of adds energy to the system, then what will happen is that there will, because energy is conserved here, you will excite some slowly decaying hydrodynamic-like mode. Like essentially, in this model, energy would diffuse. And so what you'll find is that if you had some state that changed the average energy, then that energy difference would diffuse, and you would see that. So the statement that you lose memory of the initial condition is not completely true, because conserved quantities always impose some long memory on, you know, what happens in the system. But you could consider a different version of this model where you actually pulse the Hamiltonian. You like apply one term, then another term, you break energy conservation, then you'd find even that goes away. Good question. Other questions?
Is this oscillation due to finite volume impact?
Yeah. This will get smaller as you made the system larger. And you can test that using the code I provide. Now, what about how long does this last? Well, so here I plot actually the recurrence time measured numerically for very small sizes because it's really hard to see this. So here I plot system size on the x-axis and the log of the recurrence time. So that means that, you know, if this is linear, approximately linear in system size, that means the recurrence time is e to the n. That's an extremely long time. So even at 5 sites, you know, this is I think like 10 to the 6 or 10 to the 7, some really huge number. And at 6 sites, my computer won't find it. It just gives up. This red curve is a prediction assuming something about the spectrum of the system for the average recurrence time. So if you wait many, many recurrence times and you count how many they occur on average, you get a curve like this for the initial state that I showed you, this plus y. And so, I mean, I wouldn't take this too seriously, but they reasonably agree with each other on these small sizes. Okay. So now I want to give you a sense of, so that's sort of the introduction to the phenomenon. And now what I want to do is I want to take a step back from quantum and go to classical and remind you what happens for a classical mini-spin system. How does chaos manifest in that case? Okay, so here's an insanely short review of classical chaos for classical spin chains. So the setup is the same. I changed the name of all the sigmas to s's, and I changed the square brackets to curly brackets, and I call them Poisson brackets. The parameters are all the same, and the basic rule is that the Poisson brackets of different spins, this is very similar to the commutator rule, except that well, it's very similar to the commutator rule. In fact, it's essentially identical. And the other rule that you need to know is that the time evolution of observable is given by its Poisson bracket with the Hamiltonian. So let me look at the same thing. And actually, this model can be obtained from the previous model by replacing the spin halves with spin j's and taking the limit j goes to infinity. In a special way, you rescale things in a certain way, and you'll actually get this spin model out. So this is actually, in a certain sense, the classical limit of the quantum model on the previous transparency. Okay. So here's our first sort of look at classical chaos. So here I now plot just the value of the component of the spin in the y direction on site 1 as a function of time for two different initial configurations. One where the spins are all up in the y direction, and one where I rotate by a very small angle, 10 to the minus 4, in the xy plane. So S1, configuration S1 is just all the spins in the y direction. Configuration S2 is all the spins in the y direction, but with the first spin rotated by 10 to the minus 4 in the xy plane. And so what you see from this plot is that at early time, actually there's a lot of coherent oscillation, and the two configurations look essentially identical on the scale that I've shown here. However, after some time, it takes a little while for the difference to manifest, but after some time, the difference starts to manifest, and the two curves diverge from each other. And they start to look also kind of chaotic. They're sort of oscillating sort of semi-randomly, and they have completely different temporal behavior. Okay. So this picture here is sort of like the classical version of thermalization, if you like. The thermal value, the thermal expectation value of this observable in this state is, again, actually, it's like an infinite temperature state. So the expectation value is 0. It means you just average over all the spins randomly. And so if you kind of time average this oscillation here, you'll find you get something pretty close to 0. I didn't show that, but that's what you'll find. And so they both kind of time average to 0, but their particular trajectories are different and kind of chaotically looking. Okay. Now, when I ask people what, let me ask you, what do you think is what's the essence of chaos? Or what's the first thing you think of when you think about chaos? Anybody, Sensitivity initial conditions, right? The butterfly effect. I think that's what everyone thinks about. Maybe almost everyone, I don't know. So let's look at that sensitivity. So here I'm going to plot now the inner product of the two spin configurations on a particular site. I'm going to take 1 minus that, and I'm going to divide by this small angle that I rotated the initial configuration by. And because it's a cosine, because it's a small angle, the difference is like 1 over theta. It's like theta squared. So that's why I divide by theta squared here. And so you see at early time, on site 1, this particular combination is pretty close to 0. It's an order 1 because they differ by an amount of order theta squared. However, so the first there's some time. This is sort of machine precision here. It's not, I'm just solving the ordinary differential equation, which is the Hamiltonian equation of motion for this spin chain. And there's some machine precision, don't worry about that. And then eventually it picks up, and what you see on this log linear plot is up to these substantial fluctuations, you see essentially a linear growth on this log linear plot, which means that these two quantities are deviating exponentially fast from each other. the difference between configuration 1 and configuration 2 is growing exponentially in time. And moreover, if I look on a site that's further away from where I made the initial conditions different, say I look at a site halfway down the chain, then it takes longer for this deviation to turn on, but eventually it does turn on, and it grows again with some chaotic rate. And this is a sort of very noisy measurement of this exponential growth, but nevertheless, there is a clear linear trend. And if you clean this up a little bit, this kind of linear trend would define what's called a Lyapunov exponent. And a Lyapunov exponent is essentially measuring how rapidly initially close trajectories diverge as a function of time. And so here I'm showing you explicitly, this is for 100 spins. Classical spins are easier to do than quantum spins. So this is for 100 spins. You see very clearly a linear trend in the separation. And as I go to further away sites, it takes longer, but eventually the chaos also turns on there as well. Well, sorry, you mean this, like how long it takes for this? Yeah. Yeah. This time difference is physical. I mean, they're both physical, but this one is sort of like some kind of propagation in space of the chaos. And this initial one is sort of the time it takes even on a single site for this very small difference to manifest. So somehow, I could try to solve this differential equation with higher machine precision and resolve this region. And if you make this smaller and go to higher precision, you can get a larger regime of exponential growth. If you average things over initial conditions, you can clean up these oscillations and you can extract a clean notion of the Lyapunov exponent. Okay. So the final thing I want to talk about is the spatial spread of chaos, which is already hinted at by Masanori's question. Suppose now I do this initial condition rotation, but on the middle site, so on site 50 of this 100 spin classical chain. And now I plot space here and time here, and I take this inner product that I was looking at before between the two different initial conditions, and I average it over different initial conditions. So here I'm averaging over the infinite temperature ensemble, so I just randomly choose spin configuration on every site. I evolve it in time. I compute this kind of thing, and then I do it again for many different initial conditions, and I show a plot of that as a function of space and time. And so what you see, first of all, is that looking at the single site, there is some initial time and some growth regime here where the difference between configuration 1 and configuration 2 is growing. Right? So that's the analog of this growth region here. However, as I look further away, if I look at a site 80 here, instead of 50, if I go 30 units away, then I go up as a function of time. It actually takes longer for the chaos to manifest itself. And that's reflected in the separation between this blue curve and this red curve here. Okay. So what I'm trying to convey with this figure is that in this system, chaos spreads ballistically in space. Right. So there is the sort of Lyapunov growth, the exponential growth that I showed you on a single site. But in terms of how it spreads between sites, that spread is ballistic. Okay. And so we're going to see, especially in the next lecture, which of these features are manifested in the quantum system, and how to extract, how to see that this chaos is spreading ballistically. Is it spreading ballistically? How do we measure that? Is there a notion of Lyapunov exponent in the quantum case? I already showed you the analog of this figure. And how do we understand these different classical notions? Do they have any quantum analog in this spin chain? I just chose it there. Yeah. Sorry, I just mean I have 100 sites of a classical spin chain, and so space is just the site number. So there's like, you can see that there's little bars here. That's just the discreteness of the space.
Right. So this S1 and S2, they're on the same site, or they are?
No, so it's a function of it's this variable again. So it's S1.S2 on site R. So I have two classical spin configurations, which is the spin configuration 1, which is a spin on every site, and configuration 2, which is a spin on every site. And I can look at a single site, and I can compare the configurations on that site as a function of time. And that's what's shown here. So in order for them to differ substantially, they differ substantially first on the same site where they were perturbed. And then as I go away in time, it takes longer and longer for them to look appreciably different because the chaos has to spread. Because here they have the same initial value. So it has to sort of spread from over here to affect the late time growth. Yeah?
So the light blue region in the middle seems a bit thicker than the rest. So that would be that the Lyapunov exponent is different? Or is it just a finite size effect?
You mean like the thickness here as compared to there? Yeah, let me think about that for a second. I think it's not so much a finite size as it is like there's a difference between near the initial condition and further away. So I think this would persist even if I had like 1,000 spins, which you could do. But the thing is that once you go away from this initial point, then the thickness here will stay approximately the same.
So can you interpret that in terms of the Lyapunov exponent, which I thought it was supposed to be sort of universal, but here there would be like two chaos regimes?
Well, so what I would say is that, so there's in fact not just one Lyapunov exponent, but a spectrum of them. And in principle, this growth, that spectrum, in order to figure out how things actually grow, you need to overlap the initial condition difference with the eigenvectors of that Lyapunov exponent matrix. So you sort of resolve the initial condition difference into the different sort of eigenvectors of the matrix that defines the Lyapunov spectrum, and that tells you how things evolve. And in this model, it's essentially translation invariant except for the boundaries. So you can think of that spectrum as depending on momentum. And so this is sort of a short distance phenomenon which can be sensitive to the higher momentum part of the Lyapunov spectrum. And then as you go further away, you'll zoom in sort of on the low momentum part, and you'll get something more universal. So I think this physics here is associated with the fact that there's a spectrum of exponents. And later on, you're sort of getting dominated by the low momentum ones, which are also the largest ones. Yeah?
So will you be able to say something about quantum chaos from the behavior of the classical system?
That's a great question. So the question was, will I be able to say something about quantum chaos from the behavior of the classical system? So what you can definitely do is say something about quantum chaos of the large spin, but still quantum mechanical system, based on the chaos of the classical system. And that's actually a theme which goes back a long ways in the quantum chaos literature, is relating the quantum mechanical properties of the wave function of the energy spectrum to the chaotic properties of the classical system, which it's the limit of, or which is the limit of it. So here, like if you wanted to study this PQIM for large local spin, then its properties will be related to the properties of this thing. But when I take the limit that the spin is 1/2, which is really like the most quantum it can be, then there's no guarantee that there's any relationship. Maybe the coarse features may be similar, but there's no guarantee that you'll have the same physics. Yeah.
You choose open boundary conditions.
Yeah.
Why didn't you use periodic ones? Which could be
You can.
any technical reason? Or no?
So for the spin chain, for the classical chain, you definitely, you can in either case. For the classical chain, I can do such big systems that it wouldn't matter. For the quantum case, when you make it periodic, you essentially have the time scale, you have the dynamic range, because things can go in both ways around. So it just you have more boundary effect, but you have less time window. So it's just a convenience because I can't do very large size. But nothing I say depends crucially on that. So we have a little bit of time left. So let's go back to the quantum case now and start seeing some of the manifestations of chaos, start to see some of this physics in the quantum case. Okay. And we'll explore this more fully the next time. So here again is the spin chain. The S's are back to being sigmas, so they're back to quantum. I have the same parameters. And here is again is the physical picture. I have some initial state, and I'm going to evolve it in time with unitary time evolution. And the first thing you can ask is, before I showed you an example of one observable, which quote unquote looked thermal at late time. Now, instead of looking at just one observable, I could look at some more macroscopic property of the system, like the entropy of subsystems. So remember, this is a pure state initially. This is all plus y state. So when I time evolve it, it remains pure. So the entropy of the whole state is 0. But the entropy of subsystems can be non-zero. And so that's what we're going to look at now. We're going to look at how the entropy of subsets of the qubits depends on the size, the number of qubits that you take, and the time. And this will give us a stronger notion of the effects of thermalization and the sort of generation of entropy that I claimed was one of the hallmarks of chaos. So here I show you as a function of time on the x-axis, on the y-axis the entropy of intervals starting from 1, I'm going up to site x for different colors corresponding to different values of x. So blue is x equals 1, it's just the entropy of the first site. This orange is x equals 2, it's the entropy of the first 2 sites. First 3, first 4, first 5, first 6, first 7. This is on a 14-site chain. Okay. So what do we see? Well, I guess the first thing you probably see is that all the entropy, the rate of change of entropy as a function of time is approximately linear. And the slope is essentially the same for all the different size regions. However, the value at which the regions saturate, so the entropy grows for a while and then saturates, the saturation value depends on the region. And what is that saturation value? Well, for the first site here, the saturation value is approximately 1. And what is 1? Well, if the first site was in a maximally mixed state, it's 1 qubit, there's 2 states, maximally mixed, the entropy is 1 bit. Similarly, the second site, the maximum value again is pretty close to 2. Now I have 2 qubits. The maximally mixed state of 2 qubits has 4 states, so the entropy is 2 log 2. Log 2 base 2 is 1, so it's 2 bits. Similarly, for 3 sites, it's approximately 3. For 4, it's approximately 4. And then as you get larger, as you get closer to half the total system size, it starts to be less and less like the thermal value. Now, why do I call this the thermal value? Remember, I showed you that rho infinity, the maximally mixed state, is the thermal state corresponding to the average energy of the initial all plus y state. So what that means is that the entropy of that thermal state for small regions, for subsets, it just scales like the number of qubits in the subset. And so what we're seeing is that the time evolution of the subsystem entropy, the entanglement entropy in this quantum state, is actually approaching the thermal value quite closely for subsystems that are not too close to being half the total system. And what's special about half? Well, because this is ultimately a pure state, it means the entropy of sites more than a half is the same as entropy of the same region less than half. Right? That's what's true for a pure state. The entropy of A and the entropy of its complement are equal. Because the chain has reflection symmetry, the entropy of 5 sites here and 14 minus 5 sites there is the same, because they have to be equal, and the reflection symmetry guarantees there's no difference. Yeah?
Can you compare this asymptotic value with a power random entropy?
So, I mean, it's just the value of a maximally mixed state. It's like this value, if you look on the computer, this is like 0.997. This is 1.998, 2.99, and then up here it starts to get, you can see by the time you get to 7, you actually don't even have 6 bits of entropy. You have fewer than that.
Yeah, exactly. So if you take a power random pure state, you'll have some corrections, which is not the one.
Oh, I see what you're saying. Yeah, yeah. No, I didn't actually do that comparison. So, yeah, I didn't do that comparison. That's a good question. Yeah, Frank.
The energy is conserved,
That's right.
and so you can never kind of reach the full.
Yeah, yeah, for sure, for sure.
So what was the energy?
The energy here is 0.
And this is in the middle of the spectrum? So
Yeah, it's in the middle of the spectrum. So this gives you a more global sense of thermalization. And it ties into this idea I was trying to push, that chaos is sort of about the generation of entropy. The loss of memory of the initial condition. If you don't know which initial condition you started with, it may as well average over them, and then you have entropy. And that's sort of what we saw in the classical chaos case, is that, you know, if you don't keep very precise track of where you started from, you're not sure where you ended up at. And so this kind of loss of memory is indeed one of the key essences of chaos. Yeah? No, this is linear. This is all linear. So the time it saturates is proportional to R. So this is an example of a time scale that grows with system size. So whereas the time for the local observable to saturate was time of order 1, the time for the entropy of half the system to saturate is the time of order half the system. Yeah?
Can you relate the slope there with Lyapunov Exponent?
Not obviously, but they may be related. So in the classical case, there is a relation between Lyapunov exponents and a notion of entropy growth called the Kolmogorov-Sinai entropy. And there you can show that the Kolmogorov-Sinai entropy is the average in phase space of the positive Lyapunov exponents. Here, we don't really even have a definition of the Lyapunov exponent spectrum, much less a quantum Pessin theorem or any of these things. So we could conjecture that, but it's not clear what it means. I won't talk about it in detail here, but there are some relations, say in ADS-CFT, between this growth rate and the Lyapunov exponent. I mean, they're proportional, but I would say it's not clear in general. So it's a good open question that you should work on. Let me be a little more precise about this idea of information coming in and going out. So the idea is, you know, we sort of said, you know, we flip a spin on the first site. How does that perturbation spread? And we saw that as it spreads, it also gets sort of spread into many degrees of freedom and becomes hard to detect. Can we quantify that a little more precisely? So suppose we put some information in here. That is, whether the spin is up or down or in some arbitrary quantum state here. Where is that information located in the final state? This is a more information theoretic way of characterizing the way that chaos spreads information out and sort of leads to a loss of memory. And well, to do this, I'm going to show you a little trick that's very useful in quantum information, which amounts to tracking information by entangling the system with a reference. So the way that trick works is I pick out one of the sites here, let's say the first site, and I pick another qubit, which I bring in from the outside, and I entangle the reference, which is this red qubit, with that first site. I put it into a bell pair. So here's my bell pair. And as a function of time, nothing happens to this qubit. So it just sits there. It's an oscillated box in your lab. You entangled it at first, and now it just doesn't move as a function of time. However, the rest of the system does evolve in time. And so what you can do is you can ask, where is the entanglement between the reference and these degrees of freedom as a function of time? So clearly at time 0, the entanglement is with the first site. But as this chaotic dynamic spreads information out, the entanglement will also spread. And to do that diagnostic, a very useful way of thinking about this is the mutual information. So remember, the mutual information is defined for a region R, which is the reference here, and some region X, which is a subset of these spins. The mutual information over 2 is the entropy of the reference plus the entropy of the site, this collection of sites, minus the entropy of the combination. And I divide it by 2. The reason I do that is because when this is equal to 1, that essentially means that R and X share one bell pair. So it's a sort of useful information theoretic diagnostic of where the entanglement has gone. If I can find a set of sites X such that this quantity is 1, then that means essentially that R and X share one bell pair. Okay, so here is that mutual information as a function of time for a single site. So I'm looking at the reference. I'm looking at mutual information between the reference and one other site in the chain. And you see, as I look at this as a function of different sites, the first site is initially maximally entangled with the reference, so the mutual information divided by 2 is equal to 1. However, as a function of time, that mutual information very, very quickly decays down to approximately 0. Okay. So you could think of this as a version of the decay of that Pauli Y operator as a function of time. Now, if you look at other sites, 2, 3, 4, well, 2 turns on after some little while, 3 turns on a little bit later, 4 a little bit later still. So it looks like the information is sort of spreading out in space somehow. But I emphasize that none of these are ever very large. So it's not like the information is just moving down the line. It's spreading out, but it's also becoming more complicated. So that no single site is able to capture the entanglement with the reference. And at late time, none of the sites are entangled with the reference, which means the entanglement between the reference and the system is not located in any single site. The information has been sort of spread non-locally throughout all of the system. But we can diagnose this a little bit better by looking at a growing collection of sites. So now I'm going to do the same thing I just showed you, but for a situation where the region I'm going to consider is site 1 up to site X. I'm going to look at it as a function of X. I'm going to look at site 1, then site 1 and 2, then site 1, 2, 3, and so on. Okay. And still the reference is there. It's entangled with the first site. Nothing happens to it as a function of time. So now here is the mutual information between many sites in the reference. So the blue curve is just the first site. That's starting at 1 and decaying, just like we saw in the previous slide, decaying quickly to approximately 0. Now look at the red curve. That's site 1 and 2. So that curve stays close to 1 a little bit longer, which means there's a little bit of a window of time in which the information is more or less in sites 1 and 2, although not in site 1. It's in some collective degrees of freedom between site 1 and 2. However, after a short period of time, that also begins to decay with time, close to 0. Now look at site 3, that's the yellow curve. Well, there's an even longer period of time in which the information is more or less contained in sites 1, 2, and 3, but not in site 1 or site 2 or site 3. That's what this showed, right? The information is not in any one of 1, 2, or 3, but it is in the combination of 1, 2, and 3. So this is sort of like if you like, a version of quantum error correction happening here. The information is embedded very non-locally in this 3-qubit Hilbert space. But eventually that too decays, now to a smaller, not as small value. If you look at 4 sites, it lasts a little longer, but then also decays, but now it's not to a very small value. And then here, this is a 10-site chain, so half is 5. So once I get to 5, it doesn't decay very much. And then when you go to 6, it actually, in 7 and 8 and 9, it barely decays at all. So what that means is that the information is spreading. What you see here is that once you have more than half of the system in your possession, you always have the entanglement. So somehow the entanglement getting delocalized, getting spread out by the chaotic dynamics. But if you have more than half the system size, you can always recover it, at least approximately. So the crucial things to take away here is that the entanglement is spreading, it's being lost. That spreading is happening ballistically. These curves are sort of equally spaced. However, it's not just spreading into 1 body degrees of freedom. Remember, this curve is these are all 0. And if I did the same thing for 2-qubit sites, it also would be pretty close to 0. So it's spreading, but it's spreading over many body degrees of freedom. It's really chaos, information being lost in the many-body Hilbert space, not just a single particle motion of some degree of freedom. And then eventually, once you have more than half the degrees of freedom, you can recover the entanglement. But this is nevertheless a very strong form of information hiding. Yeah, Frank.
So how do you know that it's entanglement? It could also be classical correlation. So is that mix as a mixed state, this last side plus this 5 an entangled state? It could still be separable and still have a large visual information.
No, well here, because the whole state is pure, I know that it's... No, but because I did trace out part of the system, but nevertheless, you can distill entanglement.
How do you know?
Well, you can give a protocol to do it, which I won't talk about here. But
because the visual information is not enough.
Sure. But
The visual information is reaching the maximum value it can take, right?
yeah. I mean, this is mutual information over 2. So saying it's near 1 is enough. No, but this is the mutual information over 2. So up here, where it's near 1, that's the value for a Bell pair. So then I know that you can distill it. Yeah. So yeah, down here I'm not making a strong statement. Sorry, I didn't mean to imply. Like in the crossover region, around half the system size, you can't make a strong statement about. Yeah, sorry, I was confused at what you were asking. But up here, where it's near 1, and it gets closer and closer to 1 as you make the system bigger, then you really can distill the Bell pair.
The statement that finite temperature destroys entanglement, is it for open systems, or here it clearly doesn't follow?
Yeah, that's a great question. So the question was the statement that the thermal physics destroys entanglement. Well, where is that? How do I understand that here? And the way I would say is that, it's not an open system. So there is ultimately entanglement between the reference and something in the system. But it's sort of this plot here, which is saying that there's no simple degrees of freedom that are entangled with the reference. So if you look at any, say, 5 spins in a 100-spin system, none of them are entangled with the reference system. So in that sense, the entanglement between them has been destroyed. Between the first spin and the reference, that's gone. To access it, you would need to look at some very complicated degrees of freedom. And that's the same if you couple the system to an environment. The entanglement may not be anywhere in the original system. It's sort of in some combination of the system and environment. But if you really could act on the whole thing, then you would be able to recover it. So I would say it's more or less the same if you include the environment in some kind of like mega system. Okay? So, yeah, that's the end of the first lecture. The next time we'll talk more about early time growth, about out-of-time order correlators, about operator growth, about attempts to define the Lyapunov exponents, and about local versus non-local dynamics and how that changes the time scales. So thanks a lot.
Can you study numerically the complexity of these states as a function of time?
The question was, can you study numerically the complexity of these states as a function of time? Maybe, but it's very hard because you need to let's suppose I choose some gates or something, like some universal, like Clifford gates and some phase rotation or something. Technically, what I need to do is optimize over all possible choices of that gate, and the number of choices grows very rapidly with the system size. So maybe for like 3 spins I could do it, or 4 maybe, if I wait long enough. But for 10, it's already hopeless. So maybe some avatar of complexity, like you could imagine you allow only local rearrangements but not global rearrangements. Maybe you could calculate that a little bit more easily. But it's very difficult.
Another one?
I think Frank had another question.
No, well, I had a question because these states cannot be very complex because they can date with a low depth quantum circuit.
Log depth.
A low depth quantum circuit.
Yeah. So of course we have an upper bound, which is the time evolution. We made them by time evolution, so that's definitely a circuit to make them. But so what Shira is asking, I think, has in mind is like if I evolve for a long time. So like suppose I keep evolving in time well past the point where the entropy saturates. So suppose I evolve for, 2 to the square root of n further time. How complex is that state? And that state could be low complexity, but it could be really high complexity. We don't know. The conjecture is that the complexity will keep growing.
No, but it would be a thermal state.
Yeah.
And that's not complex.
No, it's equivalent to a thermal state, but it's not actually a thermal state. So, of course, from the point of view of local expectation values, it's a very low complexity. But as a many-body quantum state, it can be very high complexity.
Sorry, but just related to that one. So do you have an idea of what the scrambling time is in this Hamiltonian or this setting?
Yeah, I haven't really defined scrambling yet, but for this Hamiltonian, the scrambling is sort of similar to the entropy saturation time. So the time to scramble information over a set of qubits of size r is proportional to r. So it'll reproduce the ballistic growth of chaos that you saw in the classical spin chain. Yeah, Fernando.
Okay, so you have some notion of velocity. You said this ballistic growth of chaos. Is there anything that can move or any signal that can propagate in the system faster than that? Or can you bound that? Can you compare this to the Lieb-Robinson bound on the velocity?
Well, it depends on how you measure. I mean, how you want to define this. But like, if as later you define it using commutators, then Lieb-Robinson will provide an upper bound on this velocity. So does that answer your question?
Well, okay. So Lieb-Robinson is a mathematical upper bound.
Yes.
But can you actually find something in the system that propagates as fast as this or faster?
I mean, it depends on what you mean a little bit by propagate. Like, if you look at like some excitation, like you try to make a sound wave or something, that'll just immediately die away. Because it's not, it has this lattice which breaks the translation symmetry and it's strongly interacting. So like, there's not like propagating modes besides energy diffusion, which moves very slowly. So in that sense, there's not like a well-defined collective mode that will move at this speed. But the rate at which entanglement spreads out is sort of given by this velocity. So in that sense, there is an operational meaning to it, which I'll actually show in next time. Yeah, Daniel.
I wanted to make a comment regarding Shira's question, just to sort of like announce a negative result I got that I'll never publish anywhere. Probably that if you try to like distinguish states at time 12 versus 14, they should be different complexities, but it's hard to find the complexity you're saying. So let's say you hand me a state at either time 10 or time 100, right? Hypothetically, those are very different sorts of states because they're very different complexity. Not very different, but different. So you might wonder whether you can tell whether you can distinguish those states. And you can't use any local measurements because it's thermalized. But you might try to train a big neural network to try to distinguish those two types of states.
Okay. Okay, so I guess I should give up distinguishing them. So I'm also a neural network. Okay, maybe I have a chance.
Okay, let's thank the
Thanks.